September 1944. Normandy, France. The stench of burnt metal and churned earth hung heavy over the battlefield of Normandy. Among the wreckage of Allied and German armor, amidst the grim detritus of war, lay the hulk of a Panzer IV OSF. Its gun barrel askew, its tracks half buried in a shell crater. It was not a victim of a direct hit, nor a catastrophic explosion. Its demise was more mundane, yet no less final: a shattered road wheel and a twisted torsion bar. For Captain Alistair Finch, a composite character similar to our previous metallurgist but now a mechanical engineer, a British mechanical engineer attached to Allied technical intelligence, this particular Panzer IV was a morbidly fascinating specimen. His mission? Dissect the enemy's war machines, understand their strengths, and more importantly, expose their fatal flaws. Finch was a man of precise measurements and cold logic, his uniform often smudged with grease and mud from his relentless inspections. He moved with a quiet intensity, his gaze analytical, seeing past the superficial damage to the underlying engineering. "Another one, Captain?" remarked Sergeant Major Tompkins, a veteran tank mechanic, as he gestured to the crippled Panzer. "Seems these Hun machines spend more time breaking down than fighting. Always the tracks, the wheels, the bloody suspension." Tompkins' observation was not mere anecdote. Allied intelligence reports from the Normandy campaign were increasingly highlighting a peculiar trend: a disproportionately high number of German tanks, particularly the Panzer IV and Panther, were being abandoned or captured not due to direct combat damage, but due to mechanical failures, especially in their running gear. The suspension systems, the intricate network of road wheels, torsion bars, and shock absorbers, seemed particularly vulnerable. Finch ran a gloved hand along the bent torsion bar, its metal groaning under the residual stress. These torsion bar suspension systems were legendary for their smooth ride and off-road capability, theoretically superior to the Allied vertical volute spring suspension, VVSS, used on Shermans. The Germans boasted of their advanced engineering, their meticulous design. Yet the evidence on the ground suggested a glaring disparity between boast and reality. "The Germans claim these tanks can withstand anything the terrain throws at them, Sergeant Major," Finch replied, pulling out a caliper to measure the diameter of the fractured torsion bar. "Yet here we are. This isn't battle damage, this is fatigue." His team began their painstaking work. They carefully disassembled the damaged suspension components, extracting fractured torsion bars, bent road wheel axles, and chassis mounts ripped from the hull. Each piece was meticulously tagged, photographed, and prepared for transport back to Allied research facilities. Back at a makeshift workshop in a recently liberated barn, equipped with basic testing apparatus, Finch and his engineers began their preliminary analysis. They cleaned the samples, examining them with magnifying glasses for clues of the material's failure. They were looking for the unseen stress points, the microscopic cracks, the telltale signs of inferior material or hurried assembly. The initial findings were subtle, yet disturbing. While the design of the torsion bar system itself was indeed robust, the material told a different story. The fractured surfaces of the steel components often displayed a crystalline, brittle appearance, rather than the ductile, fibrous fracture expected of high-quality alloy steel. "Look at this, Captain," said Lieutenant Evans, a junior engineer, peering through a small field microscope. "The grain structure here, it's inconsistent, and there are signs of slag inclusions, poor forging." Finch adjusted the microscope. The microstructure of the steel, especially in the critical torsion bars and the welds holding the suspension mounts to the chassis, was far from ideal. There were indicators of insufficient alloying elements, particularly nickel, chromium, and molybdenum, which were crucial for steel toughness and resilience against impact and fatigue. "Inadequate tempering," Finch murmured, a frown deepening on his face. "And possibly, the steel itself is not up to specification. They are making compromises." This was the chilling implication. The Germans were building tanks that looked fearsome, tanks that had superior armor and firepower. But beneath the surface, in the critical load-bearing components of their suspension, they were betraying their own engineering principles. Their wartime production pressures, their desperate need for tanks, were forcing them to make fatal mistakes that were killing the reliability of their best armor. "If this is widespread, Sergeant Major," Finch told Tompkins, showing him a fractured torsion bar, "then these Panzers are not being destroyed by our anti-tank guns as often as we thought. They're breaking their own backs. Their Achilles heel isn't their armor, it's what's holding them up." The broken backbone of the Panzer IV was a silent killer, more insidious than any anti-tank round. It rendered the tank immobile, a sitting duck for Allied artillery or infantry, often miles from the front lines, without ever seeing combat. And the British engineers were about to expose this fundamental flaw, turning Germany's technological pride into a strategic liability. October 1944. Remy Workshops, Aldershot, England. The captured components from the crippled Panzer IV were meticulously transported to the Royal Electrical and Mechanical Engineers, REME workshops in Aldershot. Here, in a sprawling, well-equipped facility, Captain Alistair Finch and his team could conduct a far more exhaustive analysis. Their findings confirmed the preliminary observations. The steel used in the critical suspension components, particularly the torsion bars and the associated mounting points, was alarmingly inconsistent. The fracture surfaces of the torsion bars, when examined under powerful microscopes, showed classic signs of brittle fracture rather than ductile failure. Instead of bending or deforming significantly before breaking, the steel simply snapped. The tempering process is clearly inadequate, Dr. Evelyn Reed, a metallurgical expert now collaborating with Finch, explained, pointing to micrographs of the steel. The steel itself isn't necessarily poor in its raw form, but it hasn't been properly heat-treated. It's too hard, too rigid, and therefore too brittle. It can't absorb shock. Tempering is a crucial heat treatment process that increases the toughness and ductility of steel, making it less prone to brittle fracture. It reduces the internal stresses that build up during quenching, rapid cooling. For a component like a torsion bar, which constantly twists and absorbs immense shocks as a tank moves over uneven terrain, proper tempering was paramount. The root cause Finch's team discovered from captured German engineering documents and interviews with POWs lay in Germany's desperate wartime industrial context. Facing critical shortages of high-quality alloying elements, nickel, chromium, molybdenum, and immense pressure to maximize tank production, German manufacturers often cut corners. This included reducing the duration or even omitting critical tempering steps to speed up throughput. They sacrificed toughness for production speed, Finch concluded, reviewing the lab results. They needed more tanks on the front, faster, so they rushed the heat treatment, and now their tanks are breaking down. This was a profound, fatal mistake. The Germans prided themselves on their advanced engineering, their over-engineered Panzers, which were theoretically superior in many aspects to Allied designs. They believed their thick armor and powerful guns made them invincible, but the Achilles' heel was not in the visible might, but in the invisible metallurgy of their suspension. A torsion bar in a tank suspension is under constant dynamic stress. Every bump, every turn, every jolt sends shock waves through it. If the steel is brittle, it cannot flex and absorb these forces. Instead, it accumulates microscopic fatigue cracks that eventually lead to catastrophic failure. Finch's team replicated the conditions in their labs. They subjected captured Panzer torsion bars to cyclical stress tests, simulating battlefield conditions. The results were stark. Many of the German torsion bars fractured after significantly fewer cycles than their British or American counterparts, and often with minimal prior deformation. Their theoretical load limits are irrelevant if the material itself can't handle the dynamic stresses, Finch stated, presenting his findings to senior Allied commanders. A German tank might look formidable, but its backbone is dangerously fragile. The tactical implications were immense. It meant that a significant percentage of German tank losses were not due to direct anti-tank fire, but to self-inflicted mechanical breakdowns. Tanks would be abandoned on battlefields, stuck in ditches, or simply rendered immobile far from the front lines, merely from traversing rough terrain or attempting rapid maneuvers. This explains so much, remarked Major General Arthur Currie, a Tank Corps veteran. We kept hearing reports of Panzers just stopping, sometimes with no apparent damage. We thought they were out of fuel or out of ammunition. This newfound understanding changed Allied tactics. While anti-tank guns and aircraft would continue their vital role, Allied tank crews and infantry were now also briefed on exploiting this mechanical vulnerability. The goal was not just to destroy the tank, but to immobilize it, force it over rough ground, lure it into quick turns, or simply wait for its own flawed engineering to betray it. The brittle torsion of the Panzer suspension was a silent killer, working insidiously within the German war machine. It was a testament to the desperate compromises forced by total war, and a fatal flaw that would ultimately hobble the German Panzer divisions, turning their technological superiority into a logistical nightmare. The backbone of the German armored might was indeed breaking, not from Allied shells, but from its own inherent weakness. November 1944, Western Front, Belgium. The advance through Belgium was a grind. Mud, cratered roads, and stubborn German resistance tested Allied logistics and resolve. For the German Panzer divisions, however, the continuous movement and the harsh terrain were proving even more destructive. Reports from captured German officers and intercepted radio traffic painted a grim picture. A significant percentage of their precious tanks were failing mechanically, far from the front lines. General Major Hans von Kleist, a composite character representing a German Panzer division commander, experiencing the growing frustration, commander of a Panzer division, paced anxiously in his command post, a commandeered farmhouse. His maps were littered with pins marking enemy positions, but even more pins marked his own tanks, broken down, awaiting recovery or abandonment. "Another 5 Panzers, Herr General," his operations officer reported grimly. 2 with shattered torsion bars, 1 with a collapsed road wheel assembly, and 2 more awaiting repairs for severe suspension damage. They are 20 kilometers behind the lines. Von Kleist slammed his fist on the table. 20 kilometers, not by enemy fire, but by our own damned roads. How can we fight when our tanks spend more time in workshops than on the battlefield? This was the rough ride that was crippling the German armored forces. The very terrain they had to traverse, the very roads and fields they had to defend or advance through, were becoming a more potent enemy than Allied anti-tank guns for a significant portion of their fleet. The fatal mistake of compromising on steel quality and tempering for speed of production was now manifesting as a strategic disaster. While the super-heavy tanks like the Tiger and Panther suffered from overly complex and heavy designs that strained their drivetrains, even the workhorse Panzer IV, supposedly simpler and more robust, was succumbing to the brittle suspension. The constant jarring, the repeated stresses of combat maneuvers, and the relentless driving across uneven ground were exposing the hidden flaws in their torsion bars and chassis mounts. This was a silent killer, operating not with explosions, but with material fatigue and structural failure. It rendered tanks immobile, turning them into targets or forcing their abandonment, thereby depleting German strength without a single Allied round being fired. November 1944, Aldershot, England. Captain Alistair Finch's intelligence was now reaching every forward-deployed Allied unit. Briefings for tank crews, infantry anti-tank teams, and reconnaissance units included specific details on the Panzer's suspension vulnerabilities. The instructions were clear: exploit the terrain, force the enemy to move rapidly over rough ground, and aim for immobilization. Remember, lads, a British tank commander lectured his crew, pointing to diagrams of a Panzerwaffe underside. You don't always need a killing shot. A track shot or a hit that damages the running gear can be just as effective. These German giants break down easily. Let their own shoddy engineering do half our work for us. Allied commanders were starting to factor this into their strategic planning. They knew that pushing the Germans hard, forcing them into rapid retreats or counterattacks across unfavorable terrain, would generate additional tank losses from mechanical failure, compounding the effects of direct combat. December 1944, Ardennes Forest, Belgium. The German Ardennes offensive, Hitler's desperate gamble, began in a blizzard of snow and a hail of shells. The initial breakthroughs were swift, as panzer divisions pushed through the thinly spread American lines. But as the panzers plunged deeper into the heavily wooded, rugged terrain of the Ardennes, the familiar specter of mechanical breakdown began to haunt them. General Major von Kleist, now leading a new division, felt a surge of hope turn to despair. His maps were again filling with breakdown symbols. The rough, icy forest roads, the steep inclines, and the constant maneuvering were taking a terrible toll on his tanks. "Herr General, another 2 Panthers immobile," a radio operator reported, his voice tinged with desperation. "One with a broken torsion bar, the other a seized road wheel. They are blocking the advance." Von Kleist cursed. "This cursed forest, this cursed steel. We are losing more tanks to the ground than to the Americans." The bitter cold of the Ardennes winter only exacerbated the problem. Brittle steel becomes even more brittle at low temperatures, making the substandard torsion bars and welds even more susceptible to catastrophic failure. The very conditions that favored a surprise offensive, the bad weather grounding Allied air power, were also revealing the profound internal weaknesses of the German armored spearhead. American troops, initially reeling from the surprise attack, quickly learned. They set up roadblocks, mined key junctions, and used their anti-tank weapons to target the Panzer's tracks and suspension, knowing that an immobile German tank was as good as destroyed. The rough ride of the Ardennes, combined with the fatal flaw of brittle suspension components, played a crucial role in grinding the German offensive to a halt. Tanks that should have been spearheading the charge were instead stranded, blocking vital roads, their crews often abandoning them for lack of repair parts or recovery vehicles. The backbone of the German armored force was indeed breaking, not just from Allied fire, but from its own inherent weakness. The broken backbone was a silent killer, turning Germany's proud tanks into immobile behemoths, destined to rust on the battlefields of Europe. The British engineers had exposed the flaw, and the Allied forces were now brutally exploiting it. February 1945, Eastern Front, Pomerania. The Eastern Front was a meat grinder, a landscape of endless snow, mud, and ceaseless combat. For the German panzer divisions fighting desperately against the Soviet behemoth, the operational environment was even more brutal than the West. Here, vast distances, minimal infrastructure, and extreme cold pushed tanks beyond their breaking point. General der Panzertruppe Dietrich von Greim, a composite character representing a high-ranking Panzer commander. A hardened veteran of years of brutal fighting stared at his operational maps with a look of profound weariness. His division, once a formidable spearhead, was now a shadow of its former self, its strength constantly hemorrhaging not just from Soviet shells, but from within. "Another 8 tanks immobile today, Herr General," his chief of staff reported, his voice flat. 4 Panzer IVs with shattered torsion bars, 3 Panthers with completely seized road wheel assemblies, 1 Tiger with a broken drive, sprocket mount. Von Greim closed his eyes. "And how many of those by enemy action?" "Only 2, General. The rest, mechanical failure." This was the unseen attrition that was systematically destroying the German armored forces. For every tank lost to a Soviet T-34 or an anti-tank gun, 2 or 3 more were breaking down due to faulty suspension components, unreliable transmissions, or overworked engines. The extreme cold exacerbated the problem, making brittle steel even more fragile and causing lubricants to congeal. The fatal mistake of prioritizing quantity and speed over quality in critical mechanical parts was now exacting a devastating toll. The initial, impressive appearance of German tanks, their thick armor and powerful guns, masked a profound internal weakness that was slowly but surely grinding their operational capacity to dust. While German propaganda continued to laud the unmatched quality of their panzers, the reality on the ground was a nightmare of logistical breakdowns. Recovery units were overwhelmed. Spare parts, already scarce due to Allied bombing, were consumed at an unsustainable rate. Tanks that could have fought were simply abandoned, immobile targets for Soviet infantry and artillery. April 1945. Western Front, the Ruhr Pocket. The war in the West was drawing to a close. Allied armies, having pushed through the Siegfried Line, were encircling the last major German forces in the Ruhr industrial heartland. The terrain was heavily industrialized, crisscrossed by canals, shattered roads, and bomb craters, a nightmare for tank movement. Captain Alistair Finch, now attached to an American technical intelligence unit, was once again on the ground, examining the wreckage. The sheer volume of abandoned German armor was staggering, and the pattern was depressingly familiar. "Another Panther here, Captain," an American sergeant called out. "Looks like it just threw a track. No penetration, no serious damage otherwise." Finch approached the Panther, a formidable beast, its 75mm gun still pointed menacingly. He examined the broken track and the twisted road wheel assembly. The torsion bars underneath were clearly fractured. "Classic fatigue fracture, Sergeant," Finch confirmed, pointing to the jagged edge of the broken steel. "Too brittle, couldn't handle the strain of turning in this rubble, probably just snapped." This was the ultimate validation of Finch's earlier research. The unseen attrition had crippled the German panzer divisions precisely as predicted. The tanks that were supposed to defend the Reich to the last were breaking down under their own weight and the demands of the terrain without ever firing a shot in their final defense. The statistics from captured German records, now being meticulously compiled by Allied intelligence, painted a stark picture. Over 30% of Panzer IVs were lost to mechanical failure. For the Panther, that number often exceeded 50% in certain campaigns. Even the mighty Tiger Yayan Batailles, while less prone to suspension failure due to over-engineering, suffered from equally crippling transmission and engine breakdowns. The broken backbone was not an isolated incident. It was a systemic plague. Germany's industrial capacity, stretched to its breaking point, had been forced to use inferior materials and rushed production methods. This had created a fatal flaw in the very core of their armored might. Allied commanders now understood that their pressure on the German logistical tail, combined with relentless combat, worked synergistically with the inherent mechanical fragility of the panzers. Every mile of rough terrain, every rapid maneuver, every defensive shift contributed to the silent, unseen attrition that slowly but surely ground the German armored divisions to dust. The Germans had built tanks that looked invincible, but in their desperation, they had inadvertently engineered their own defeat, one brittle torsion bar and shattered road wheel at a time. The unseen costs of compromised quality had finally led to total military collapse. July 1945. Daimler-Benz factory, Stuttgart, occupied Germany. The vast Daimler-Benz factory, once a symbol of German industrial might, now lay partly in ruins, partly under Allied control. Among the sprawling assembly lines and machine shops, a team of British and American engineers, led by Captain Alistair Finch, meticulously sifted through blueprints, production logs, and remaining material samples. Their goal, to precisely pinpoint the systematic nature of the fatal flaw in German tank suspension. Finch and his team uncovered mountains of damning evidence. Intercepted memos from German high command revealed directives pushing for increased tank production at any cost. This pressure translated directly to compromises on the factory floor. Suppliers of special alloy steels were continually under strain, often forced to deliver batches that did not meet original specifications. "Look at this," Lieutenant Evans, Finch's assistant, exclaimed, holding up a production log. For the Panzer IV torsion bars in late '43, they reduced the nickel content by nearly 30% and cut tempering time by 25%. Finch examined the log, his face grim. There it is, the direct link. They knew they were making compromises, but they had no choice. The war demanded numbers over integrity. Interviews with surviving German engineers and factory managers painted a vivid picture of the impossible dilemmas they faced. Under relentless Allied bombing and severe resource shortages, they were constantly forced to make ersatz, substitute materials work, or to streamline heat treatment processes to churn out tanks faster. "We protested, Herr Captain," one elderly German metallurgist, Dr. Ernst Schmidt, recounted, his voice weary. "We warned the Reichsministerium that these compromises would affect reliability, but the answer was always the same: produce more. The front demands it." Dr. Schmidt explained that while the raw steel for the Panzer IV chassis itself was generally good, the crucial components like the torsion bars, road wheel axles, and even the pins connecting the track links required specific high-grade alloy steels and precise heat treatment. Without sufficient nickel, chromium, and molybdenum, and without proper tempering, these components became brittle and prone to fatigue, fracture under the constant dynamic loads of a moving tank. "It was like building a house with magnificent walls," Dr. Schmidt concluded, "but using brittle nails for the framework. It looked strong, but the framework would eventually fail." This was the weight of compromise, the heavy, unseen burden that Germany's desperate industrial policies placed on its own war machine. Every percentage point of reduced alloy, every minute shaved off a tempering cycle, accumulated into a systemic vulnerability that crippled their armored divisions. Finch's final report to Allied High Command synthesized these findings into a clear, damning indictment of German wartime production. It conclusively proved that material shortages, critical alloying elements were chronically scarce, production pressure, unrealistic quotas forced manufacturers to cut corners, compromised quality. This led to brittle steel in crucial suspension components. Systemic failure. This wasn't isolated, it was a widespread, inherent flaw in their most important tanks. The report estimated that over 30% of all Panzer IVs and well over 50% of Panthers were lost to mechanical breakdown, particularly suspension failures, rather than direct enemy action. These figures were staggering, representing an immense, self-inflicted strategic attrition. General Dwight D. Eisenhower, Supreme Allied Commander, reviewed Finch's report with a grim satisfaction. "So the enemy was fighting himself as much as us," he remarked to his staff. "Their own shortages, their own desperation, created weaknesses we didn't always need to exploit directly." The knowledge gained from Finch's investigation profoundly influenced post-war tank design. It underscored the critical importance of material science, comprehensive component testing, and avoiding compromises in critical load-bearing structures. The broken backbone of the German Panzer became a permanent cautionary tale for military vehicle designers worldwide. The weight of compromise had finally crushed the German armored divisions. Their fatal mistake was believing that the impressive facade of their tanks could compensate for the fundamental weaknesses in their internal components. The British engineers had meticulously exposed this flaw, revealing how Germany's industrial desperation had ultimately turned its most feared weapon into its own greatest liability. Post-war. 1946. Lecture Hall, Royal Military Academy, Sandhurst, England. Captain Alistair Finch, now a major and a respected figure in military engineering, stood before a new generation of British tank officers. Behind him, a large diagram of a dissected Panzer IV suspension system was projected, its torsion bars, road wheels, and chassis mounts clearly labeled. The war was over, but its lessons were paramount. "Gentlemen," Major Finch began, his voice calm but authoritative, "for years the German panzer divisions were seen as almost invincible. Superior armor, powerful guns, formidable tactics. But a significant, often overlooked factor in their ultimate defeat was a hidden weakness. An Achilles heel, if you will." He pointed to the diagram. "This, the suspension system. Specifically the torsion bars, road wheel axles, and the welds securing the entire assembly to the hull. Our investigations, conducted during and after the war, revealed a systemic, fatal flaw." Finch then walked the cadets through his findings. The design was good, on paper. The torsion bar suspension was conceptually sound, offering a stable platform and good off-road performance. The materials were flawed. Due to wartime shortages, German manufacturers were forced to use lower-grade alloy steels, particularly lacking in nickel, chromium, and molybdenum, elements vital for steel toughness. The manufacturing was rushed, Critical heat treatment processes like tempering were shortened or omitted entirely to speed up production. This left the steel dangerously brittle. The consequence was catastrophic. Under the constant dynamic stress of combat maneuvers, rough terrain, and especially the shock loads of unexpected impacts, these brittle components fractured. These weren't battle scars, Finch emphasized, holding up a fractured torsion bar recovered from a Panzer. This was self-destruction. This torsion bar, designed to twist and absorb immense energy, simply snapped. Like glass. He cited statistics from captured German records. Over 30% of Panzer IVs were lost due to irreparable mechanical breakdowns, primarily suspension and drivetrain failures. For the heavier Panther tanks, which put even greater strain on their running gear, this figure often exceeded 50% in many campaigns. Even the mighty Tiger tanks, while less prone to suspension failure, suffered from equally debilitating transmission and engine breakdowns due to similar material and manufacturing compromises. Think of it, Finch continued, a German tank perhaps miles from the front suddenly immobilized because a road wheel collapsed, or a Panther spearheading an attack grinding to a halt because a torsion bar snapped. These tanks weren't defeated by a direct hit from an anti-tank gun. They were defeated by their own structural integrity failing under the weight of combat. This was the Achilles heel of the German Panzer divisions. Not their armor, not their guns, but the very system designed to move them across the battlefield. Their desperation for numbers had led them to compromise on the invisible yet vital components that gave their tanks life. Finch then showed the cadets photographs of countless abandoned German tanks across Europe, many with no obvious battle damage, simply stuck in ditches, on roadsides, or in fields, their running gear visibly shattered. These were the ghosts of the unseen attrition, the silent casualties of Germany's fatal mistake. The German High Command, blinded by their faith in their superior engineering and desperate for more tanks, had consistently refused to acknowledge the systemic nature of these breakdowns. They dismissed them as isolated incidents, crew error, or battle damage. This refusal to accept a fundamental flaw in their own equipment contributed significantly to their strategic defeat. The lesson, gentlemen, Finch concluded, is this. True strength lies not just in visible power, but in unseen integrity. A formidable facade means nothing if its foundation is brittle. The German Panzer, for all its might, ultimately carried its own destruction within its suspension. It was its Achilles heel. The cadets, future commanders of Britain's armored forces, absorbed the lesson. The strength of an army depended not just on courage and firepower, but on the relentless pursuit of quality, even in the smallest, most overlooked components. The broken backbone of the Panzer had taught the Allies a vital lesson. Sometimes the enemy's greatest weakness is one they unwittingly create themselves. Post-war, 1950s onwards, the battlefields of Europe fell silent, but the lessons learned from the shattered remnants of German Panzer tanks echoed for decades. The meticulous work of Major Alistair Finch and his teams of British engineers and metallurgists left a lasting imprint on military vehicle design, engineering standards, and the understanding of the true costs of industrial compromise in wartime. The broken backbone of the German Panzer, once a closely guarded Allied intelligence secret, became a foundational case study in engineering academies worldwide. It was a stark example of how a nation's industrial capacity, its access to strategic raw materials, and its willingness to compromise on quality can directly determine the operational effectiveness and ultimate fate of its most formidable weapon systems. For Finch, who returned to a quiet career in industrial metallurgy, his wartime discoveries were a testament to the profound impact of unseen details. He often lectured on the tyranny of the small part, emphasizing that a tank's ultimate strength was only as good as its weakest, most compromised component. The humble torsion bar, made of brittle, substandard steel, had inadvertently played a crucial role in the outcome of the European War. The thousands of abandoned German tanks across Europe, many with no obvious battle damage but with telltale shattered suspension components, stood as silent monuments to this fatal flaw. These were the unseen costs of Germany's desperate war effort, a stark reminder that strategic defeat could be engineered not just by enemy fire, but by internal collapse. The German High Command's fatal mistake was multifaceted. Overconfidence in design. They believed their advanced designs, like the torsion bar suspension, would compensate for material shortcomings. Underestimation of dynamic stress. They failed to adequately model the cumulative, brutal forces of continuous combat operations on compromised materials. Suppression of warnings. Internal reports of mechanical failures were often dismissed or ignored due to the overwhelming pressure for production and a reluctance to admit systemic flaws. This combination created a strategic vulnerability that Allied forces expertly exploited. They learned that forcing German tanks to move rapidly over rough terrain, engaging them in prolonged maneuvers, and pressuring their logistical tail amplified the inherent mechanical fragility of the Panzers, driving up their breakdown rates. The legacy of the Panzer's Achilles heel directly influenced post-war tank development. Future tank designs across the globe placed an even greater emphasis on robust material science, the selection and rigorous testing of alloy steels for critical components, comprehensive stress testing, simulating extreme battlefield conditions, including thermal shock, dynamic loading, and fatigue cycles for all components, logistical reliability, understanding that a tank's combat value is inextricably linked to its ability to stay operational and move across the battlefield. The Panzer, despite its impressive armor and firepower, was ultimately hobbled by its own inherent weaknesses. The broken backbone of its suspension systems became a tragic metaphor for Germany's overall war effort, formidable on the surface but internally crumbling under the relentless pressure of a two-front war and a collapsing industrial base. The story of the British engineers and the German Panzer suspension remains a powerful testament to how scientific investigation, seemingly far removed from the battlefield, can uncover critical insights that shift the tides of war. It teaches us that victory often lies in understanding not just an enemy's strengths, but the profound self-inflicted wounds they carry within. The famous German blitzkrieg was ultimately slowed and often stopped, not just by Allied resistance, but by the brittle torsion of its own legendary tanks. This brings us to a final thought-provoking question for our audience. In modern military conflicts, what do you think are some of the hidden weaknesses or unseen costs that might plague advanced military hardware today, similar to the Panzer's suspension flaws? Share your insights and observations in the comments below. I read every single one.